Hello to my lovely viewers who I am sure are subscribed to my non-educational channel. Top link in the description. Welcome to the full exponential function review for AP Precalculus. This video just takes my exponential function videos from Unit 2 and plops them into one video, so best of luck learning! Topic 2.2 is a kind of clarification on sequences and an introduction to exponential functions. So, sequence equations we talked about last video. You could probably tell I don't really like them because of my tone talking about them last video. However, before we get into this video, I need to clarify something on particularly these two equations. I said last video that the zero term was the first term of the sequence. What would have been more appropriate would have been to say that it is the initial term, because it's technically the term before the first term. If you're still confused, reference the answers to the questions at the end of my last video and they will clarify it. So anyway, though I don't really like these equations, they do tell us some stuff. And a massive surprise to everyone, I'm sure, an arithmetic sequence is really just a linear function. And we see that in its equations, as the form a sub n equals a sub 0 plus dn is really just the equation y equals b plus mx, which is the linear function equation. And the other equation, a sub n equals a sub k plus d multiplied by n minus k, could be expressed as another way of writing linear equations, being f of x equals yi plus m multiplied by x minus xi, where you include the point xi comma yi in the equation. Geometric sequences embody a new type of function we'll be talking about this unit, exponential functions. The exponential function skeleton equation is f of x equals ab to the power of x, and you can see the similarity to the geometric sequence equation. And funny enough, the second geometric sequence equation can be transformed into an exponential function, written as f of x equals yi multiplied by r to the power of x minus xi, where it includes the point xi comma yi in its equation. So what do we take away from all of this? Well, here it is. Linear functions have output values changing at a constant rate based on addition, and exponential functions have output values changing at a proportional rate based on multiplication. Which is why if you see a graph, table, or even just 2 points, you should be able to tell me whether it is exponential or linear. Exponential functions themselves are a next video. Topic 2.3 is all about exponential functions and their properties. Lots of students seem to struggle with exponential functions in math. So to those kids I say, they really aren't that bad, just wait till we get to log functions. But anyway, we already know the skeleton equation to an exponential function is f of x equals ab to the power of x, where a is the initial value and b is the base. And take a look at the graph. It's a curve that keeps curving. There are 3 simple rules of an exponential function. First is that a can never equal 0. The second is that b must always be positive. And finally, b can never be 1. Other than those 3 things, you can do really whatever you'd like with the function. An exponential growth happens when a is greater than 0 and b is greater than 1. It looks like this on a graph. You can see it growing, hence it being called a growth. An exponential decay happens when a is greater than 0 and b is less than 1 but greater than 0. It looks like this on a graph, and you can see it decreasing, hence it being called a decay. I don't want an exponential function graph to trick you though. Despite it looking like it's curving up, it is still going to positive infinity on the x-axis. This means all exponential functions will have a domain of all real numbers. Some other fun things. An exponential function is either always increasing or decreasing, meaning it is only concave up or down, and never changes. This also means that exponential functions have no points of inflection. Exponential functions are a little weird though, because they don't have an ironclad parent function. The parent function of an exponential function is said to be b to the x, where b is greater than 1 for a growth, or between 0 and 1 for a decay. So that means that any value you plug into b that is greater than 1 or between 1 and 0 falls into the group of being a parent function for the exponential function. And for these parent functions, we can see some fun things. First is that no matter what, there will always be a point at 0, 1, because anything to the power of 0 is 1. The second thing we see is that there is a horizontal asymptote at y equals 0, and this would mean the limit as x approaches negative infinity of any growth parent function would be 0. And of course, as x approaches positive infinity, all growth parent functions would approach positive infinity. The end behavior of any parent exponential decay functions would simply be swapped from the growths. But where the horizontal asymptotes are and what the end behavior is are all impacted by the transformations of a function, which is an issue for next topic. 2.4 is all about different rules to do with exponents and how those rules impact exponential functions. So for this video, we will learn 4 properties. We'll go in order and start with the first one, the product property, which says that b to the m multiplied by b to the n is equal to b to the m plus n. So what to take from this is that if you multiply 2 values with an exponent that have the same base, or b, then you are really just adding their exponents. To explain this one on a graph, we'll start with the parent function y equals 2 to the power of x. If we change this to y equals 2 to the power of x minus 1, we see the whole graph shift to the right by 1, making adding or subtracting anything from the x a horizontal translation of the graph. The second property is the power property, which says that b to the m to the power of n is equal to b to the mn, meaning if you have double exponents, you are simply multiplying the exponents together. What this does to a graph is it functions as being the stretch or shrink value to the graph, meaning it is the horizontal dilation. Students sometimes are confused how to sketch a graph that has dilations. My advice is to simply make a table and graph that information to make it easiest. But anyway, the next two properties move away from graphs. The first one is the negative exponent property, which states that b to the negative n power equals 1 over b to the n. This means that if you ever have a negative exponent, it is simply equal to 1 over the original term, removing the negative sign on the exponent. Finally, we have the last property, which doesn't really have a name, so for our cases, we're just going to call it the exponent root property. It states the following: b to the 1 over k is equal to the kth root of b. This means that if you ever have a power that is 1 over something, it's really asking you to do what the denominator's root of the function is. So for example, this equation is really asking what the third root of 8 is, which is 2. And that is really all. 2.5 is all about building exponential functions from scenarios. Now listen, this isn't complex. You can tell an exponential function is a best fit for a scenario if you see it based on multiplication, and you should already know how to build an exponential function from my topic 2.2, 3, and 4 videos, and you should know how to model from scenarios from my topic 1.13 video, so I'm not going to simply repeat everything I said. There is, however, a lot of other things from this topic we need to talk about. Understand that you only need to be given 2 points, or dare I say input-output value pairs, to derive an exponential function to fit the model. You do this by solving a system of equations which you should have been taught how to do back in algebra, but if you still need help with it, here is 2 examples of me solving systems of equations with exponential functions, and use the transformations discussed last video to mess around or tweak exponential functions to what the questions are asking. Also understand that exponential functions are used and written in different ways to represent interest and compound interest in real life, with b as the growth factor. And though you don't need to memorize these interest equations for the AP exam, they are often required for schools throughout America to teach, which is why they're on the screen right now. This all leads into e. E is a massively long number that we're going to round to 2.718. E is the base of a natural exponential function that is used to model continuous growth or decay in real-life scenarios, like continuously compounded interest. Unlike regular growth factors, E is special because it allows us to model processes that change at a rate proportional to their current value. E is a complex topic and takes a while to understand, but it's not that crucial to understand for the AP exam. One thing that is crucial is how to model exponential functions on calculators. And just as you have all the polynomial regressions, you also have the EXP regression you can run to see if your data is exponential, so keep that in mind. Oh boy, done already? Well, that's alright. Do me a favor and click on this end screen here. It's a great video, I promise. Come on, man. Please? Please?